All right, so let's talk about the pressure measurements. Now, pressure is defined as the normal force exerted by a medium, which is usually a fluid, a liquid, or a gas on a unit area. Now, this is typically detected as a differential quantity, which means we generally measure the difference between the unknown pressure and the known reference pressure. All right, where the most common reference pressure for the typical applications is the atmospheric pressure. So now the differential quantity or the differential pressure that we measure is actually referred to as gauge pressure. If the reference pressure is taken to be 0, then the pressure that we measure is called as the absolute pressure. And if the pressure we measure is less than the atmospheric pressure, that actually is referred to as the vacuum. Now we can write it here. So gauge pressure is equal to the pressure measured minus atmospheric pressure. And here in the absolute one, we have the absolute pressure is defined as the pressure measured with 0 reference. If we just try to understand this from this figure, so let's say this is the absolute 0, defines this horizontal line, then this is the atmospheric pressure. Suppose this is the pressure of the fluid that we're measuring. Now this would be the absolute pressure, and this is defined as the gauge pressure. So typically we measure the gauge pressure because it gets easy for us whenever we try to measure pressure in terms of a differential quantity, that the atmospheric pressure is always available to us, which is a standard value of a pressure. And in these differential kind of devices, we generally makes easy for us to determine the gauge pressure. We can always add the atmospheric pressure to find out the absolute pressure. So this is the difference. So we have absolute pressure and the gauge pressure. Now vacuum is something where the liquid or the gas, let's say, or any chamber or whatever we want to measure, the pressure is somewhere here. Now it's obviously less than the atmospheric pressure, so this is referred to as vacuum. But we do have a high vacuum where this pressure is quite close to the absolute 0, so we may refer to it as high vacuum. Now this is also measured, this can also be measured as an absolute pressure like this or like this. We do also measure it as a negative gauge pressure also, where we measure it in this way. So for example, a gauge pressure of, let's say, -2 atmosphere or something like that, or it could be of some value, would actually refer to the vacuum. Otherwise, in general, the gauge pressures that we get, let's say, or it could be, let's say, in pascals, if we write in pascals or megapascals or whatever units of pressure are, so we can write a positive value of, let's say, 1.013 10 to the 5 pascals. This is 1 atmosphere, so we can write something like this, which means 2 times the atmospheric pressure is the gauge pressure. All right, and the absolute pressure obviously would be this 2.013 10 to the power of 5 pascals plus the atmospheric pressure, which is 1.013 into 10 to the power of 5 pascals. All right, so this is the terminology. We generally use the gauge pressure terminology, or we can use absolute pressures, but because we generally deal with differential quantities, so obviously in that case the reference, if the reference exists as atmospheric pressure, which is generally easier, so we would measure is what is called as the gauge pressure. Fine. Now the standard atmospheric pressure is defined in the sense of hydrostatic state of, or hydrostatic pressure, as the pressure exerted at the bottom of a mercury column. So right, pressure exerted at the bottom of mercury column, 760 millimeters in height. All right, so that's why the standard atmospheric pressure is also written sometimes like this, 760 mm of Hg. Now this will be equals to 1.01325 into 10 to the power of 5 pascals, or which is also equal to newtons per meter square, which is the unit of pressure. All right, now this measurement of pressure actually is very important in the determining of net loads on the pressure vessels and the pipe walls. So we do as instrumentation, let's say engineers, or let's say as the students of instrumentation, measurements and instrumentation, find this as a very important mechanical properties associated with the some of the major applications in the industries or in our day-to-day life or in the societies, where the pressure measurement becomes significant, or the monitoring of pressure becomes significant. And this pressure obviously could be sometimes very kind of a low pressure, or it can be always a high pressure. So also all such things are very important in our day-to-day life. Now again, putting it in the more of a text form, so pressure measurement is important in the laboratory and the industries, since it's one of the most important variables that affects the processes. For example, in the IC engine cylinder, the pressure varies continuously with time, and that determines the power output of the engine. Or the chemical reactions that are affected by the operating pressure. In the thermal power plants, the operating pressure of the boiler, you must have studied in the applied thermodynamics, needs to be closely monitored during the operation. So the importance is that it's an important property that describes a thermodynamic system. It's invariably important process parameter, and this difference is sometimes, or it's many of the time, used as a means of measuring the flow rate of a fluid also. So the flow rate and the pressure of a fluid actually are interdependent. So that's why measuring pressure difference would also give us the measurement of the flow rate of the fluid. That's why this also becomes one of the application of the importance of the pressure measurement. Now, so this is the range. So it spans from the subatmospheric, which could be the vacuum that we were just talking about, to very high pressure, several thousand times the atmospheric pressure. So we have gas pipelines, we have water pipelines, which sometimes are which sometimes do have a very high pressure, let's say fluid, or you can say water, or you can say any other, let's say fluid going through them, so which leads to very high pressures. And obviously you may have sometimes subatmospheric pressures also. For example, in the medical arena, or in various other applications, we do have the subatmospheric pressures also. So that's why different sensors are to be designed, or that are available to cover this range of pressures met with in the practice. Also, measurement of pressure transients would require an understanding of the transient response of the pressure sensor. The other applications are to measure the altitude for planes or weather balloons. So we don't really measure the altitude in terms of measuring the height, rather we measure the pressure with the weather balloons. and that would give us the altitude. There's a relation bearing that. And then we also obviously have discussed just now, we can, in conjunction with the Venturi effect, we can measure the flow. The Venturi effect can measure the flow, so measuring the altitude. Also we can use it to measure the depth of the water. Now this is the range and the type of pressure gauges, or the type of transducers, or you can say the type of devices that we do use. So we do use something called as a resistance gauge. We have a Bourdon tube gauge. We have diaphragm based pressure gauges. We have Bellows type pressure gauges. We have piezoelectric type. Manometers are very popular. McLeod gauge, and we have Pirani gauge, and we have ionization gauge. So these are some of the different types of gauges that are used popularly in the measurement of pressure. What is important is that if you look at the lower limit and the upper limit, so this is in the millimeters of mercury column. So we can correlate it with the pascals, or you can say the SI units. So this is a very low pressure measurements are also there, which are done by, let's say, ionization gauge, and we have Pirani gauge, and we also have the McLeod gauge. So these are all three are generally for the low pressure measurements. And the Bourdon gauge, or the resistance type of gauge, or maybe even the diaphragm bellows, we may even the piezoelectric. So these may span into the high pressure measurements. So we have something called as high pressure, we have a low pressure that we have to measure, but we do also have something called as the static and dynamics, or you can say dynamic pressures, which means fluid at rest would exert a pressure obviously on the walls, but fluid in motion would exert probably more, let's say, pressure on the walls, and it does have, it is obviously different from what we call as the static pressure. So we do have to see which type of gauge would be suitable for even such things. So we may have a very high pressure, a pipeline, but the sometimes it could be static case, but we may even have a low pressure one. It could be dynamic in, as the input. So the dynamics has to be taken care of. For example, this thing came out of my mind, out of the manometer. So manometers are generally very popularly used as the pressure gauges, but they do have problems when the dynamic pressure measurements are to be done. For example, which means if the pressure to be measured is actually changing with time, so it varies with time. So manometers, may not be really suitable, for such things. They may show the changes, but they may not be really suitable for such purpose. So we do have to make the design based on these things also, as we have also already discussed in the design of instruments. Now these are some of the units of the pressure. So we do make use of pressure into the Pascal. So this is from Blaise Pascal, the scientist. So we have 1 Pascal is equal to 1 Newton per meter square, force per unit area. The atmospheric pressure is defined as the 760 millimeter of mercury column, which is also equal to 1.013 10 to the power of 5 pascals. The 1 millimeter of mercury column, which would mean actually subatmospheric, because if you just see atmospheric pressure is 760 mm of mercury column, which means, let's say, the standard reference pressure. But 1 mm would mean quite low, or very small amount of pressure actually, which is subatmospheric, or what we have defined as the vacuum. So we do make use of something called as torr, 1 torr, as the units for such vacuum pressures. We don't generally use these units like pascals. For that, we make use of something like TORR. But obviously, we can even write everything in terms of the standard SI units, which is Newton per meter square also, where the torr could be converted back in this form. And then 1 bar is also similar to the atmospheric pressure. So this is equal to almost 1 atmosphere. This is also a standard unit for pressure. Now let's come to the static and dynamic pressure. So whenever we see in a pipeline, for example, this is our pipeline in which the fluid is moving. It could be liquid or gas. Now we do have a pressure in this vessel, but because of the given velocity of the liquid flowing through the pipe, we do have something called as the kinetic energy associated with this fluid. So we have two components of pressure at this point rather than at this point. So we have this pressure measurement is generally taken in this case if we want to measure the flow or the liquid flow velocity of this liquid. So if we do make use of such things, you must have studied about pi2 tube, so which we put up here. Then we assume that the fluid that goes through this tube gets stagnated, and then whatever pressure is there, the static and the dynamic pressure associated with the fluid, that gets converted into the column of the the mercury, or column, column of the fluid in this you can say pipe, which can be taken back through the transducers. Now the velocity profile inside this, if we just try to draw the velocity profile, it's very popularly, you must have you must remember this type of profiles associated flow through pipes. So the velocity at the boundaries is generally assumed to be almost negligible. So because of that, what it means is that the pressure at this point is just due to the static, let's say, part of the pressure, and then pressure at this point is higher, which is actually composed of the both static and the dynamic pressures. So in this case, there is pressure associated due to the kinetic energy also. So now this gets converted into the height of the liquid. So this pressure that is measured through pipe A would actually be the total or the stagnation pressure. And the pressure measured at point B, in which the velocity is almost zero, so the kinetic energy component would be almost negligible. So we do have pressure at this point, but this is just due to the static component. So tube B would measure the static one. All right, so we call this as impact tube A and static pressure tube B. So tube A would sense the total or stagnation pressure, and the dynamic pressure component would be equal to stagnation pressure minus static pressure, or you can say the stagnation pressure is nothing but static pressure plus dynamic pressure. So this dynamic pressure is due to the kinetic energy of the fluid, which is proportional to the velocity of the fluid. So we can get the velocity from here, and then we do get mass flow rate also, which is Q, can get from this relation. All right, so we do have the two types of pressure that can be measured here. One is the static one, and another is the dynamic one. So because of this thing, we can basically measure the velocity of the fluid also. So which would mean actually that we do have to take care of the static and the dynamic pressures in the measurement of pressure. So it's not just the pressure that the static pressure that we are measuring, but the dynamic component is also important, and the instruments would also have to be designed accordingly. Now these are the pressure measurement devices that are generally used. We do make use of manometers, Bourdon gauges, diaphragms, and bellows, very popularly used. We have inductive and maybe capacitive pressure transducers. We have some special device for high pressure measurement and the low pressure measurements. Manometers are very popularly studied as the kind of YouTubes. You can say the YouTube manometer here. All right. So where we place a liquid, or you can call it as a manometric fluid, and then we have another liquid or fluid or whatever gas that we have whose pressure is to be measured. One end of this is actually left to the atmosphere, so that would give us the atmospheric pressure on this side, and then this is the pressure of the liquid this is the liquid whose pressure is to be measured. So then we can basically again find out the difference between the 2 points, and then that is found as the height of the mercury column that is raised. So if the pressure is atmospheric on the both sides, so we would see that at any section this level of the mercury would be same. As this pressure increases or goes beyond the atmospheric pressure, above the atmospheric pressure, so this would push it down, and then this would raise the height of the manometric fluid on the right side, and then the height of the liquid that is raised, or the manometric fluid that is raised, is equal to the pressure difference between the two ends. Because we know the atmospheric pressure, so we can find out the pressure of the unknown, or the given liquid that is to be measured. Now, so we can write it down here. The manometry measurements of pressure by comparison to the hydrostatic pressure produced by the column of liquid. So these, why are these popularly used? Because you can see advantages. These are very simple, inexpensive, and relatively free from error. The disadvantages or the limitations are we pressure ranges are limited. That depends on the manometric liquid density also, and also the poor dynamic response. It just measures pressures almost up to, can say, the ranges less than 200 kilopascals or 30 psi. It's the typical manometer that measures, but we do obviously have changes, or can say improvements in these also. And these are popularly used, that is true, but obviously there are obviously some limitations, and we do have some other alternatives associated with the manometers. Before going to the next one, I can just maybe write it down here. So these are the relations that we generally use in the manometer. So we have P1A minus P2A is equal to the height into density of mercury minus density of the liquid whose density is to be measured into the acceleration due to gravity. And it's very important to understand that in manometers we put them vertically. We employ them vertically rather than horizontally, because this is the height of the liquid, and then obviously the hydrostatic pressure would be due to the gravity, the gravitational, the mass of the liquid that is raised. So that is actually, the weight of the liquid that is raised upon the area of cross section, that is the actual pressure. So weight would exist only if there is acceleration due to gravity. So that's why we would generally, put these manometers vertically. All right. And now from this equation, so what we have is P1A minus P2A is equal to, so if this is not the atmospheric one, so let's call this as P2A, and this is P1A, is equal to the height of this into the density of the mercury here, all right, into the height into G minus PT. So if there is a liquid, let's say there's a liquid which has a different density, if we're not putting air from this side, so if there is a liquid of different density, so obviously that is rho T. So this is actually derived from this one, this balance. So P1A plus rho T GH is equal to P2A plus rho M GH, where rho M is the manometric density of the manometric fluid, and this is the pressure at this point. So in this case, we can balance it here. So this is P1A plus rho T GH, this one, is equal to P2A plus rho M GH. So from this we can get this, and if the pressure on the other side is the atmospheric pressure, so obviously it becomes P1A minus P atmospheric is equal to H into the density of manometric fluid minus density of the other fluid. And if the other fluid is generally, it could be sometimes air, and the manometric fluid density is very high, so in that case rho M is generally very higher than rho T. In that case we have P1A is minus P atmospheric pressure is equal to H rho m into G, which is a popular equation that we see in the for the manometers. Fine. So now this tells us that the a simple U-tube manometer will have a greater pressure range when a more dense measuring fluid is used. So now this pressure range, the difference between the two pressures, or this will be very high. Obviously, this will correspond to small h, but if the rho m, because this is directly proportional to the difference of the pressure, if this is high, so then the pressure range is also will also be high. So for measuring, even what it would simply mean that if you want to measure a very high pressure, with the manometers, but obviously we have limitations. But if you want to measure a high pressure, increase this limitation, then what we would have to do is we'll have to use a different fluid, which is having density much higher than the mercury also. But obviously that comes at the cost, obviously. So there again we have to do some trade-off, but this is what this equation would mean. And we have something called as sensitivity. Sensitivity would be defined by h upon delta p, so which is this h upon delta p. So this would be 1 by rho mg is equal to 1 by rho m into g. So if g is constant, so our sensitivity would depend inversely on rho m. So which means if we increase the density, the sensitivity will decrease. So that's why again we have to do kind of some trade-off. So a greater sensitivity we can say is achieved, which is equal to change in the height per unit change in the pressure when a less dense fluid is used. So जितना हम less dense यानी बहुत ही लो डेंसिटी फ्लूइड यूज करेंगे, यानी उससे हमारी सेंसिटिविटी तो बढ़ेगी, लेकिन उससे हमारी प्रॉब्लम क्या होगी, हमारी जो प्रेशर डिफरेंस और जो प्रेशर मेजरिंग रेंज है वो कम हो जाएगा. फॉर एग्जांपल इफ वी यूज वाटर ओनली, so water will also be helpful for us. But what would happen as the pressure increase this water, because of the low density, we may not be able to measure larger difference of pressure between the atmospheric and the pressure to be measured. Obviously, when we use mercury, then we are getting a better pressure range, but the sensitivity decreases. But that's the trade-off. So if we get even a very thicker material, or a thicker liquid as the manometric fluid, then the pressure range may increase, but the sensitivity would decrease. So that's how you design instruments based on your requirements. What is your requirements? What pressure you're expecting to be measured or to be monitored? Accordingly, you design your even pressure transducers, which could be manometers in this case. Now, one more way of increasing this, let's say, this sensitivity is using these well type manometers. So we have well type inclined tube manometer or well type manometers. In well type manometers, what we try to do is that we assume one of the sides of the manometer U-tube is a well. So well here refers to a container with a bigger cross section. So which means as capital D is very higher than the smaller d. So in that case, using the some of the basic relations, again in this case, if we try to use this type of diagram, so we end up sorry, we end up with some relations like this. I'll just write down without deriving them. So P minus PA, so P minus PA is equal to the density of manometric fluid minus density of the other fluid, G into 1 plus A by A into small h. Now the small a is the area of cross section, area of the longer tube, or you can say longer and thin tube, whereas capital A is the area of well. The well. Now typically this A by A, or we say well, is kept of a larger area. This becomes almost very small. So it's typically very less or smaller than 1. Then in that case, our difference in pressure P minus PA is equal to rho m minus rho t into GH. Fine. So the good thing about this is we don't have to measure, or we don't have to visualize this end, or the well end rather. The other side only is very important for us in terms of measurement. So the height of this liquid will change, and for a pressure, a good amount of pressure difference, we may see a very small amount of change in the well. Rather, this change, this small h would be much, or considerably higher. So rather than measuring the difference, we just have to measure the changes in this h. That's the good thing about well type manometers. या इसको सिस्टर्न मैनोमीटर भी बोलते हैं. तो इसके अंदर हम सिर्फ इसको वॉच करते हैं, इसके अंदर की चेंजेस, और उसको कॉरेस्पॉन्ड करते हैं हम बेसिकली टू दी प्रेशर डिफरेंस. रादर देन यूट्यूब वाले में जो है, हमें ये भी ये सेक्शन हमें पता होना चाहिए, या ये सेक्शन हमें पता हम कहाँ से ले रहे हैं. तो सपोज हम ज़्यादा प्रेशर लेते हैं तो ये ऊपर जाएगा, लेकिन ये भी उसमें नीचे जा सकता है. तो हमें फिर वहाँ से वहाँ तक डिफरेंस को लेना है. लेकिन इस केस के अंदर हम क्या करते हैं, बिकॉज ऑफ द लार्जर वेल, so we assume this height, or this small difference is very, so this height change in the well is very small because of the larger cross sectional area. So we approximate it with just this right side measurement, where how much it has gone up. Accordingly we find the, or we relate it to the pressure difference. So we also modify this as a well type manometer, but we make use of something called as inclined tube manometer. So this inclination, what it actually is useful in is that if we try to derive again a similar relation, so we have something like this: P minus PA is equal to rho M minus rho T. This is the rho. I'm just writing the rho symbols. I hope you are not confusing it with L. Then we have G into sine theta plus A by A into R. Sine theta, where theta is the inclination angle, small a is the area of cross section of this tube, capital A is the cross sectional area of the well, and then we have R as, let's say, the length that is to be, let's say, measured in this case. Again, we have P as the pressure, input pressure, PA as the atmospheric pressure. This is the relation. So with this type of arrangement, what we can do is, can say that inclination of this tube actually basically it amplifies the measured quantity, and hence improves the precision of the instrument. Now these types of levels in manometers are obviously measured by visual inspection, or you do have some other optical methods of also measuring these levels, where you can basically connect it to the computer. We have something called as non-visual or high resolution capacitive interferometers, or ultrasounds can be used to measure these levels. So this is the good thing about manometer. But I'm just maybe coming back to this part. So why, what advantage this gives us to is, it will help us to increase the precision, because we with this this inclination, we have an amplified kind of we can say amplified values for the same pressure change differences. How it impacts actually our sensitivity is, which is nothing but the L upon delta P is equal to 1 upon rho M sine theta into G. So if again we assume this rho T is very smaller than rho M, so then we have rho M G into sine theta if A by A is very small. So these are the assumptions. A by is very small, rho M is much greater than rho T. With these assumptions we reach to here. So this R, you can say R or L, here we refer to as, sorry, I put it R here, so R by rho G, sorry, R by delta P is equal to 1 by M. So our sensitivity actually will also change. So what it means that in the previous one, or you can say in the YouTube one that we had seen, the sensitivity was 1 by rho mg in this case. But in this case, we have sensitivity as 1 by rho m sine of theta. So obviously sine theta could be less than 1 most of the cases, so sensitivity would increase. So we are improving the sensitivity of this, without changing actually the pressure range by just inclining this, part of the thin, or you can say thinner part of the, manometer in this at some inclination. Fine. Now we also make use of something called as Bourdon tube gauges. So Bourdon tubes, you must have already understood on now what Bourdon tube is. So you make use of a tube which is generally having an elliptical cross sections through which, this, let's say, pressurized liquid is sent. Accordingly, it goes through this tube. All right, and then there is a mechanism attached, and then the pointer is attached. So this works again on the principle of the deformation. You can see elastic deformation of these tubes. So you design your Bourdon gauges as per the requirements of the pressures to be measured, the pressure range high to low, which is to be measured, and then it basically deforms, and then you can correlate that deformation with the pressure that is applied. You can calibrate it. So these are very old pictures of Bourdon tube gauges. These could be even, wound spiral in the spiral form also, like this, to increase its range. So this is the inlet. It goes through this, and then it goes through this, and then it has a pointer attached. So rather than just making one turn, you can make several turns in this Bourdon tube to obviously sometimes increase its range, or maybe precision also. Now these are very popularly used because they generally cover a large range of pressure measurements. Fine. And they are purely mechanical instruments. They basically utilize the mechanical deformation of the flattened bend, or you can say bent type in a spring, that winds or unwinds, maybe, and depends on the pressure difference between the inside and the outside. So in this case, the motion is against the hairspring torque. You can say that prevents any backlash in the movement. We have generally an elliptical cross section, or we call it as bent shape. So as the deformation of this occurs, generally the deformation would also happen on this cross section. So rather than elliptical, so it may turn out to be even circular as the pressure is applied. So it's designed in such a way, or it can also deform maybe. So that deformation of the cross section, or change in the cross section, would be, assisted by, moving of motion of this Bourdon tube in this form. So it will displace like this. It allows it to deform and then maybe turn out to this shape or similar to that. And that, movement of this part is actually taken up by the mechanism. And it could be a gear and a kind of a lever arrangement or a connecting link type of an attachment, crank type of an attachment. It basically amplifies that small movement of the Bourdon tube because of the pressure. All right, so this is called as the helical one, the helical Bourdon tube, or this was a spiral Bourdon tube. So these are different types of Bourdon tubes that are employed for pressure measurements. Now we do make use of the diaphragms, which are, I would say, more popular than maybe I would say any of the pressure measuring instruments these days. And these diaphragms are actually, again, in this case, we see this cross-sectional view. So this is one pressure that's to be in or it could be reference pressure, and this is the pressure to be measured. Again, what we call as the differential pressure. So this could be employed in such a way in this type of a, let's say, arrangement where we have a diaphragm, and as the pressure increases, this diaphragm deforms, and because the obviously pressure difference, this deforms, and this deformation can be correlated to the pressure difference between the two ends, which can be measured or picked up by using any of the positioning instruments like LVDT, which is popularly used in these cases. Or you can also use something called as strain gauges. that are employed on the diaphragms. So as the pressure difference occurs, the diaphragm deforms, and then accordingly we have changes in the resistance on these strain gauges, and then we have some, let's say, bridge type of arrangements which can actually tell us amount of pressure difference between the two ends. So this is again a popular way to measure pressures. So the diaphragms undergo both the tangential and, or you can say, circumferential and radial strains. So they act like kind of a spring that undergo displacement under the action of pressure. So these are popularly used, I would say, as pressure sensors. In modern times, we do make use of diaphragms, but obviously they do have limitations, or a trade-off between the cost sometimes and the amount of pressure that they can measure. But they do measure, very high pressures also. This is how these sensors look like in real world. Sorry. So this is one end of the pressure to be measured. We can leave this to the atmosphere, or we can sometimes connect it to another point to measure the pressure difference. One good example I must share with you is when we were actually doing it as an experiment. So we wanted to measure the flow rate through the pipe. So we connected a venturi meter in that. So we had a venturi meter like this, for example, and in that we wanted to measure the flow rate of the liquid. So what we did is we made a 3D printed venturi meter, and we basically had a opening here, and then we made an opening here. So these were connected to these two ends, one end and the second end. So we would assume that here we were able to measure static pressure. Again, here we were able to measure static pressure. Fine. But what happens is, at this point the velocity is of some value, and at this point the velocity is higher because of the Bernoulli's principle. Obviously, with all the assumptions that are there for the Bernoulli's principle. So we assume that Bernoulli's principle holds from here to here, and at these 2 points we assume the pressure has to remain same. So in this case, the pressure at this point, due to the kinetic energy, would be, let's say, of some value, but in this case the kinetic energy would increase. The amount of static pressure would basically decrease. Sorry. So at this point the velocity is high. I'm sorry. Control P. So at this point the velocity is very high. At this point the velocity is low, so static pressure component would be higher, and in this case the dynamic pressure will also be to some extent of some value. But at this point the static pressure would be almost like very low, because the pressure has been converted, everything has been converted almost to the kinetic energy of the flowing liquid. So this will be low pressure and this will be high pressure. So the difference in pressure actually from the Bernoulli's principle, which is the equation, popular equation, P1 plus half. Oh, sorry. Anyways, we get the velocity. We get the velocity of the flowing liquid, in terms of the pressure difference and some other things associated. So such sensors are popularly used, and obviously they do have some limitations. So in this case, you may see it looks to be a very simple sensor, but these are all almost diaphragm based sensors. That are there are diaphragms, and then there are, could be strain gauges, or it could be like maybe other small instruments, electronics is associated, which converts that to the value of the pressures. So in this slide we have something called as differential pressure, which is the difference between the two pressures introduced as input of the sensing unit, and we have absolute or gauge pressure, which can be measured. Now another way is using bellows. So bellows are again some elastic materials, sometimes of this kind of nature in the form of a cross section. So as the pressure is put up to the bellows expand, and they generally may not really contract back, but we make use of some springs, to it. So those springs actually push it back to the on the original point, or they may not sometimes be necessary to be pushed back to the original point if there's a continuous pressure that is exerted. So, so as the pressure is exerted, these bellows start to expand, again acting as the springs, and as they move, they are we connect it to the some measuring instrument like LVDT, and again we can basically measure the amount of pressure that we have applied. So this the difference in the pressure actually, we have P2 from here that goes here, and then P1 from here. So if P2 is the atmospheric pressure, so this is left out as an open ended from here. So the P amount of P1, or the difference between the two pressures, actually will cause deformation in the bellows, and that deformation can be correlated back to the pressure amount of pressure actually that is applied. So in case of bellows, we do make use of some simple equation like this: delta is equal to the difference in pressure, like this, where delta is the displacement of bellow element, A is the inside area of bellows, and K is the spring constant of bellow element. All right, so we can calibrate these bellows, and accordingly we can design them. They are also popularly used in the measurement of pressure, but obviously they may not be sorry, so precise sometimes. So we may have to go for, let's say, diaphragms and other type of pressure measuring instruments. We do make use of these inductive transducers, or also capacitive ones also, which I have not talked about here. So obviously in capacitive one also, if we just maybe theoretically see, it's nothing but we have two plates. It could be of diaphragm, and then we have dielectric between them. So there is two ends. One is connected with P, another is connected to P2. Sorry, P1 and P2. So if this is atmospheric, P2 will exert pressure on this, and this will deform like this, and that will change the distance between the two plates, and accordingly the capacitance will also change, and that can be correlated to the pressure. That is of a capacitive one. And in the inductive one, we again make use of the concept of mutual inductance, or inductance of the coils. So we have an arrangement like this, and then we make use of a diaphragm again. In this case also we have diaphragms. So there are two ends, or two openings to this instrument. So we have P1, or let's say P1 and P2. Say if this is atmospheric, this is the pressure to be measured. So as this pressure is higher than the atmospheric, this will deform the diaphragm, and accordingly the inductance will change in the two coils. So here it will be nearer to this, here it will be farther away from this. So accordingly the inductance would change, and then that can be picked up by the output circuit, and then we can basically measure the difference of pressure with this type of instruments also. Now coming to the almost last part of this lecture. So we have the high pressure measurements and low pressure measurements. This is specifically taken up here because we will discuss just one instrument in both of these cases. We do encounter such requirements where we have pressures above 1 megapascals, so which is about almost 10 times the atmospheric pressure, and which can extend upwards to the limit present of present techniques, which is of the order of 100 gigapascals, or 10 to the power of 6 atmospheres. So this is a very, very high pressure. So at this pressure, we may not be able to use, let's say, any diaphragm or any such things. That may not be really feasible. Each instrument manufacturer obviously would mention his limitations about the instrument, and this may be very high. So we may have to design different type of instrument in this case. Now, conventional techniques like using piezoelectric transducers, we have not covered it here, but piezoelectric sensors again are used in the pressure measurements, where obviously there is deformation of that crystal, and then it produces charge. So again, we can use piezoelectric for dynamic pressure measurements, that we have already discussed why dynamics is important in piezoelectric. And we can also use Bourdon tube gauges. So these are quite rugged and strong. So Bourdon tubes and piezoelectric could be used, in the measurements of very higher range. Uh, but we may have in alternate, or we do make use of some alternate techniques in this one, which is by making use of something called as electric resistance gauges. So rather than putting an impact on these Bourdon tubes, or we can say on the piezoelectric ones, we make use of a rather simpler technique, which is based on the electric resistance pressure gauges, or you can say electric change in the electric resistance. So in this case, what happens is that the, we make use of some sensing element. We'll just discuss the, the line diagram of the same also. So it consists of basically a coil, which is relatively of a fine wire. The length and cross section of where obviously we know that it's affected, affects the electric resistance, which is R is equal to rho L by A. So we know that any coil or any wire, its resistance depends on the resistivity, the length, and the area. Now, assuming the resistivity remains same, what we can think about is that if the applied pressure, which is very high pressure actually, can change or would change its length and area to some extent, or which means would change its length and diameter to some extent, obviously in the elastic range only. Now, if this thing happens, then we have change in the electric resistance. So as the electric resistance changes, we can pick up this by making use of some bridge circuits again, which can be corresponded to the or calibrated against the applied pressure. Now, this is determined, actually the change, how much change it happens is determined by the bulk modulus of the material that we use for this resistance. Now the bulk modulus, many of you must be remembering the definition. It is nothing but the change in the pressure upon the volumetric strain, which is delta V by V. So we make use of this concept where the high pressure, actually it's a very high pressure, would deform kind of this coil, and then its resistance changes, and that resistance can be picked up by the kind of a bridge circuit. In this one particular one, we have something called as bulk modulus pressure gauge. So in this case, we make use of something called as kerosene filled bellows also. So this is the pressure connection. This is the cell body, or you can say the instrument body here. It's a very high pressure that goes through this. Then we make use of bellows. We don't make this this wire that we want to use here as a sensing wire come directly in contact with the pressure. Rather, we make use of bellows. This is typically kerosene filled bellows that are put up here. So as the pressure goes here, the bellows are compressed, and accordingly there is volumetric strain associated with this, and then it also causes change in the, you can say, the thin wire of the material. Like, this is wrong spelling, so we have mang. The proper spelling I'll just put up here. Mang, MANGGANIN. So this is a material, or we also make use of gold, chromium materials. These are all called them as special alloys. They have some components of copper, manganese, nickel that are put up as the material for this wire that is used here. This is the terminal. One end is connected to the ground, another is connected to here. We measure this change in the resistance, and this is packed up in a very special kind of a setup, so that these high pressure may not damage it. But we make use of bellows, and as the pressure goes in, this compresses. There is it causes change in the length and the diameter of this coil, and accordingly it changes the resistance of this wire. So that we are already aware about those equations, that rho L is equal, resistance is rho L by A. This can be put in the form of diameter as rho L by some constant d square, because that is pi d square and all the things. So we put that as constant. And in the design of strain gauges also, we have seen this type of equation, so we can write it this way: dl by L minus 2 something like this plus d rho by rho. So this is similar to what we have already done in strain gauges. Now in this case we encounter something called as biaxial state of stress. So we have sigma x sigma y that is equal to the amount of pressure that is applied, where we have stress on the other one of the ends is 0. So we have strain associated like this. This can be correlated to this one, which is when nu is the Poisson's ratio. And this equation we have got from the popular equation for the three-dimensional state of stress. So 1 by capital E sigma x minus nu times sigma y plus sigma z. So this is a very popular equation for the strain when we have the three-dimensional state of stress. So in this case, sigma x, sigma y, because we are applying pressure of the fluid, so they will remain same. So this will be replaced by P, and sigma z we are assuming biaxial state of stress only in this case, because there won't be any stress in one of the directions. The reason can be, we can look from some resources that provides us the reasons, but obviously we can assume sigma z also to be something. That would just change this P by E 1 minus nu. These are some of the assumptions. This all leads finally to something like equation like this: dr by r is equal to 2p by E plus d rho by rho. So this, agar hum isko all three stresses can be taken, we can take all those three also, and then it will change this equation. But if we just take biaxial state of stress, it will lead to something like this. So where this is rho and this is P, which is the pressure applied. So if rho is assumed to be constant, resistivity does not change. For example, in this case, if we assume like that, then our change in resistance can be correlated or corresponding to 2 by E, which is constant, into P. So this pressure difference can be correlated to change in the resistance. But typically, that, as I said, if we take three-dimensional data, all such things, maybe other considerations also, we do make use of some equations like this for this type of gauges. These are pressures. P is pressure. So we make use of again a quadratic equation in this case. So this we have seen already, but we make use of these things, where it's a square of pressure also. That we'll have to see. But just to make sure that you don't confuse with these things. So if we assume z sigma z also to be something like P, then accordingly we will have changes in this, and then we have changes in the relation between the pressure and the resistance correspondence. Fine, those things could always be done. But the concept here is that the bulk modulus is a concept is used where we have the applied pressure change in the volume, which is volume of the material here, which is the wire, for which we assume that there is change in length and change in the corresponding diameter, obviously with the Poisson's ratio being there. So this concept is used alternatively for the high pressure measurements, though we have the Bourdon tube and the piezoelectric transducers, which can also measure a good amount of pressure, high pressure. So one more important thing is that it says that high pressure Bourdon tubes are often made with a number of turns also, and in this case we can have a high ratio of wall thickness to diameter for such pressures. Now again, to the other extreme, we have low pressure measurements. So it says that low pressure measurements are required in various applications such as airflow, static duct and clean room pressures in HVACs, that is heating, ventilation and air conditions. We do not make use of very high pressure, we make use of very low pressures, and energy management systems. Or other applications it could be like medical instrumentation, environmental pollution control, boiler combustion efficiency, and in other research and development requirements. Now, below the atmospheric pressure we refer to as vacuum, we already discussed. So the gauge pressure could be written as negative value, and we specify vacuum. So absolute pressure at that point is, however, certainly positive, because we have just seen that from the previous slides. Now we can make use of something called as, again, YouTube manometers or Bourdon gauges for this measurement, as long as it's not high vacuum. So for example, we can use YouTube manometer even for minus 70 mmHg, which means almost uh, around near about to a vacuum which is very high. So 760 would obviously mean 1 atmosphere. So it's like almost 0 atmosphere. But we do have limitations with using YouTube manometers also in this range. Uh, even subatmospheric pressures have very special instruments that can be employed rather than this rough type of arrangement. So we have something called as Pirani gauge that is used in the measurement of low pressure, where we use the concept of the kinetic theory of gases, which tells us that the temperature, as the uh, where we have a given wire. I'll just maybe write it this way rather. So we have this type of arrangement where we make use of some resistors, let's say, and enclose them in a particular arrangement like this. So we have a resistor coil here, and then we have another resistor on this side, 2 plus 2 resistors, known resistors. So we have 4 resistors, which acts like a Wheatstone bridge. One of the resistor is enclosed, or you can say that is not allowed to to be exposed to the, let's say, atmosphere. The other one is enclosed again, but this is allowed to be connected to the pressure source, which is almost a vacuum pressure, or you can say very low pressure. But what happens is, as this is exposed to this low pressure, so what happens is, because of low pressure, this current flowing through this actually will cause, sorry, the current flowing through the resistor will cause it to heat up, isn't it, by I square R losses. But because of the low pressure, which is less than the atmospheric pressure, something changes. What happens is that because of the low pressure, which means the density also is low, the coil, so that's what is written here. So the temperature of a given wire actually through which an electric current is flowing will depend on the magnitude of current, the resistivity, and the rate at which the heat is generated in the wire by resistive losses. Sorry, the heat generated in the wire by resistive losses conveyed to the environment. So जैसे हमारे पास एक वायर है, उसमें से इलेक्ट्रिक करंट पास कर रही है, तो उसमें हमारे पास आई स्क्वायर आर लॉसेस होते हैं, विच आर दी losses because of the type of conductor that we're using. So depending on the resistance of this wire and also the current flowing through this wire, we have the losses. But it's also, if we blow something like some fan over it, and it kind of doesn't heat up itself, so we do maintain some losses like this. But if we do not blow anything like this, so what happens is, after some time it becomes kind of a radiator. So it just radiates heat. So because of that radiation, because of increasing temperature, this wire also, we have maybe under this concept. So the resistance of a wire will also change with the temperature. So जैसे इसका temperature बढ़ेगा, तो इसकी resistance भी change हो जाएगी. So accordingly, ये factor तीसरा आता है कि जिस हिसाब से we can basically take away the heat generated in the wire to the environment. If we do not do that, then obviously there could be changes in the resistance. But there is another concept where we say that if we जो surrounding इसकी है, environment इसका, अगर उसका हम basically उसका pressure decrease करेंगे below the atmospheric pressure, which means the density of the the air or whatever medium is there is decreased. So what will happen is, because of continuously decreasing the density, the amount of heat that was to be conveyed to the environment is now decreasing. So what will happen because of that? There will be change in the resistance because of such, say, this type of effect. So it says that thermal conductivity of the surrounding media, the reducing the density of the medium actually decreases the conductivity. Reducing density of the medium, which could be air in this case, by decreasing its pressure, with decreasing its density, it decreases the conductivity. Let's say conductivity means the heat conductivity from the wire to the environment. It decreases that, and the wire obviously would become hotter for a given current flow. So wire will become hotter for a given current flow. It will also change the resistance. So as the change in resistance is there, by Wheatstone bridge, we can basically measure the correspondence with the pressure. Now this is popularly called as Pirani gauge. So it consists of two wires, so two resistances which are platinum filaments connected to one arm of the bridge. The other arm has the other two known resistances. So one of the resistors out of these platinum filament ones is sealed after evacuating its container, while the other is exported to the vacuum whose pressure is to be measured. Surrounding pressure changes the filament temperature and thereby its resistance. So as जैसे pressure decrease होगा almost to the vacuum, that will change the filament temperature and obviously its resistance will also be changed. Now the gauge is calibrated such as this imbalance current of the bridge is directly related to the vacuum pressure being measured. So the range is almost from 1 to 100 Pascal, which is much below the atmospheric pressure. There's always also a compensating cell, which is this one, which is again a platinum filament wire, which is used to minimize the variations due to the ambient temperature changes. So maybe there are ambient temperature changes that may impact these wires also. So we may have to compensate for those through this type of arrangement. So this was about the pressure measurements. I hope there is some knowledge gain from this lecture. This was kind of to be divided into 2-3 lectures, but because of time constraints and because of other things, I'm sorry for that. So, but I hope some of the knowledge has gone into your things. You would need obviously a revision, look at the books maybe and the other resources. If you have any doubts, you can talk to me. We can maybe clear those doubts before the exams.